All right, so another video kind of bringing up to speed on some acid base information. In this case, strength of acids and bases. And again, you may have come across this previously, but you may want to watch the video and just make sure you're up to speed on everything. I'm going to start this with a quick little demo. So without further, here we go. So what I'm going to do here is I'm going to use two different acids to illustrate how you can distinguish between a strong acid and a weak acid. So firstly, we have our 1.0 molar per liter hydrochloric acid. I'm so going to put this beaker in contact with the conductivity tester, and let's see what happens. Oh, so that's a pretty bright light. All right, for my next one, I'm going to put same concentration, 1.0 mole per liter of acetic acid in contact with the conductivity tester, and let's see what happens there. All right, so here we go. Okay, so I'm hoping you've seen the difference. You notice the difference, the distinguishing feature of those two acids, of hydrochloric acid and of acetic acid. And so those distinguishing features are this, basically. So with the hydrochloric acid, it dissociates fully. That is, all of the constituent ions, H plus and Cl minus, are now in solution. So there's more electrolytes in solution, and so it's a better conductor. With the acetic acid, there is definitely some electrolytes present. There is some H plus, there's some acetate ion, but there's not as much of it. So the concentration of the ions of both ions in acetic acid is less, meaning that in acid base parlance, or for acid base purposes, the concentration of hydrogen ion, H plus, is greater in HCl. So that becomes important later. Alright, so anyways, that's the distinguishing feature, and that's really the topic of this video, the strength of acids and bases. So let's go. So strong acids, as I said, dissociate completely. HCl, aqueous, yields H plus, aqueous, plus Cl minus, not anything else, plus Cl minus, aqueous. And so notice it's a single arrow indicating this is not an equilibrium situation. Why is that? Because it's only one direction, this reaction. We can write this with water present and look at it in terms of Bronsted-Lowry, but it's still a unidirectional reaction. Alright, you will not see a dissociation of a strong acid written as an equilibrium. And so in terms of equilibrium constants, which we're going to come across, it says here, this is your Ka column, hydrochloric acid strong. You know, some of the other values are 10 to the minus 8, that's a weak acid. 10 to the minus 4, weak acid. Here's another strong acid, nitric acid, HNO3, strong. So there's no value for K. We know the concentration of hydrogen ion. That's what we're interested in when we do an acid dissociation. All right, let's look at a weak acid, a couple other strong acids, and hydrochloric acid, sulfuric, nitric, perchloric, hydrobromic, hydroiodic. You should try to familiarize yourself with these strong acids. Sulfuric acid is kind of an interesting because it's a strong acid, so it dissociates in water. And so we get the hydrogen sulfide ion, HSO4 minus, plus the hydronium ion. Should put simple state. And so that's definitely a strong acid dissociation. So there's my amount of hydronium ion, H3O plus. But I have here the hydrogen sulfide, and that's an ionizable proton, this H plus. So it can further dissociate to SO4 2 minus aqueous. And when it does that, it also produces hydronium ion. But the sulfate ion is a weak acid. and so it does not dissociate fully. So it's actually an equilibrium situation. So you have an equilibrium between the hydrogen sulfate ion and the sulfate ion. And so this complicates things when we're trying to determine pH, because it's not a true dissociation of H2SO4 to 2 times H plus, because of the weak acid nature of the hydrogen sulfate ion. So we don't actually double the concentration of H plus. Anyways, that's for a different conversation, but just be aware that sulfuric acid is a strong acid, but it produces, in theory, only 1 mole of hydronium ion. All right. Weak acids then, on the other hand, dissociate partially. So hydrofluoric acid is a good example of a weak acid. So aqueous hydrofluoric acid plus water. And we definitely want to look at this as an equilibrium situation. So it yields the fluoride anion plus hydronium ion. And the whole thing about weak acid dissociations is, in terms of acid base, we can't tell by looking at the concentration what the concentration of hydronium ion is. That's different from a strong acid. Strong acid, 1 mole per liter HCl yields 1 mole per liter hydronium ion. Not the case with weak acid. So this involves a calculation, and we're going to do those later. But it can still dissociate, and the important thing to recognize now is it's an equilibrium situation. So there's the Ka for hydrofluoric acid. So you can see it's quite small, 6.7 times 10 to the minus 4. So the equilibrium lies far to the left in favor of the reactant hydrofluoric acid. So what it means is there's not a very high concentration of products. And you can tell that because of the Ka value. So what are the weak acids? Well, weak acids are anything to dissociate in water to produce hydrogen ion H plus, and is not one of the 6 strong ones. So there's quite a few examples you can familiarize yourself with. You'll come across some organic acids, all the carboxylic acids. They're very commonly shown or used as weak acids. So something like formic acid. So formic acid is a weak acid, and so it would dissociate partially, and so you get hydrogen or hydronium ion plus the formate ion. Hydrogen phosphate ion. So much like the sulfate ion, hydrogen phosphate, after the phosphoric acid has lost 1 proton, you would get the hydrogen phosphate ion, which loses 1 more proton and produces hydronium. And actually that's the dihydrogen phosphate and the hydrogen phosphate, which is also a weak acid. So that kind of keeps going. That's a triprotic acid. The ammonium ion, NH4 plus, is a weak acid. It has that extra H plus, so that acts as an ionizable proton, and so you get ammonia gas and hydronium ion. So those are just a few examples. There's many weak acids. There are only 6 strong, so most of the rest of them are weak. How about a strong base? So strong base, good example is sodium hydroxide. So again, strong bases dissociate fully in solution. So NaOH aqueous yields single arrow because it dissociates fully, Na plus plus OH minus. I've not seen strong bases dealt with as Bronsted-Lowry bases because it gets quite complicated in terms of the equation. So this is the very common way to write strong base dissociation, single arrow and ions. In terms of the strong bases, well, group 1 and 2 metal hydroxides, most of those are considered strong bases. And just one thing to recognize, so barium hydroxide, group 2 metal hydroxide is a strong base. There's full dissociation producing 2 moles of hydroxide ions. So don't forget the stoichiometry involved, 2 hydroxide. So in terms of concentrations, if you had a 1.0 times 10 to the minus 3 molar solution of barium hydroxide, you'd have 1 times 10 to the minus 3 molar barium, and you'd have 2 times 1 times 10 to the minus 3 molar hydroxide. So that's going to be 2 times 10 to the minus 3 moles per liter of hydroxide ion. So don't forget the stoichiometry, because again, this is the important number when it comes to acid-base calculations. Weak bases then, on the other hand, dissociated partially. So we've seen ammonium ion as a weak acid. Well, ammonia acts as a weak base. So we can definitely write this in terms of Bronsted-Lowry. It's an equilibrium, and so it becomes the ammonium ion, NH4+, and that gets dissolved in solution, plus hydroxide ion, OH-. So ammonia, weak base, dissociates only partially, and that's what the image is trying to show. Examples of weak base, we've just seen ammonia. Amines, very common weak bases. So methylamine, you should remember from organic, and that is, I'm not sure what state it is, but let's call it, I think it's going to be a gas plus water, and so it dissociates partially, so it's going to lose, or sorry, as a base, it's going to gain a proton, so it's going to become NH3 plus aqueous plus hydroxide ion, OH- aqueous, weak base. So amines, all the amines are weak bases. So there's methylamine, 4.38 times 10 to the minus 4. Again, equilibrium lies far to the left, favoring the reactants. Not much hydroxide ion produced. And then any anion of weak acid is going to be a weak base. So hydrogen sulfate, that's the anion of hydrosulfuric acid. So the hydrogen sulfate anion plus water is going to be a weak base, so it's going to gain that proton, so it becomes H2S. Actually, I think that's a gas, and hydroxide ion. And so those are a few examples of bases, weak bases. And so that's it, strength of acids and bases, based on the amount of dissociation. Fully dissociated, strong acid, strong base. Partially dissociated, weak acid or weak base. And that concludes this video.